Hello there, students. So I had wanted to go through these in class, but again, in the interest of time, since we had so much fun, I did not. So I pulled these out, and I really wanted to put them in a spreadsheet anyway, just to show you. I've already given you my written out examples, so you could probably follow it, but I wanted to talk you through it. Here's the main kinematic equations. And again, you can play around with subscripts. You can show whether something's horizontal or vertical. If it's vertical, you usually put a little X by it. If it is, vertical, usually be a Y. Horizontal, usually be an X. But they can get pretty convoluted. So I try to keep things as simple as possible. Let's go through this one. And again, I always model for you how I would like you to proceed. So the first thing that you do when you're reading a problem is you think about what variables there are and what units they might be. So it says one simple model for a person running the 100-meter dash is to assume the sprinter runs with a constant acceleration until reaching top speed, then maintains that speed through the finish line. So I would draw a picture in this case, which if you look at my work was really just a simple line diagram, but overall you have a trip part A, and then you have a trip part B. And if you wanted to visualize these, it's pretty easy to do. Let's just say travel here, and then we'll do another one. So first part of the trip, second part of the trip. So for part A here, we can say, here's the part A math. These are basically two separate problems almost, right? The only thing that keeps them the same is that we have a known, there we go, a known distance, right? This is a 100-meter dash. There we go. We know this is 100 meters between part A and part B. So that's nice. So for part A, we want to figure out what's going on here. It's going to be some fraction of 100 meters. Part B, incidentally, will also be a fraction, but the greater part of it. That's our assumption. So we know that the sprinter is going to reach their top speed of 11.4 meters per second in 2.54 seconds. So that is what we use for part A. They're going to reach this top speed, which means they probably started from rest, right? So I'm going to say speed 0, right? That's an underscore, just meant to show that this is a subscript. So speed 0 is, hey, I'm going to say it's 0 meters per second. And speed final is going to be what? It's going to be 11.4 meters per second. Again, I'm showing this to you in Excel so you can kind of follow along. You might want to model it yourself if you like Excel. If you don't like spreadsheets, then don't worry about it. And then the time it takes for trip A is given as 2.54 seconds. Notice that I'm keeping the units separate here because I want to be able to use these numbers in equations. And I'll say it one last time, I won't belabor this point, but I have all this worked out already in a screenshot of my work. So we have that, and we want to say, well, what's the acceleration? Well, we know that the acceleration is not equal to 0, but look, we can solve for the acceleration using any of the equations that actually have acceleration in it. And if you look at this equation, this is basically the definition of acceleration. Acceleration is defined as the change in velocity, dv if you will, but change in velocity divided by the change in time, or the total time here. And so acceleration is going to equal what? Acceleration will be the final speed minus the initial speed, which happens to be 0, so we technically could ignore it. Quantity divided by the time it took to change that speed. All right, and this is in meters per second or meters per second squared. So that's the acceleration, so that's great. At that point, we assume that acceleration drops down to 0. But that's for part B. We still actually haven't found the distance that this person has traveled. So we're trying to find the distance that part A represents. We know it's going to be less than 100 meters. Well, that's great. Now look, we know the time it took for part A. We know the acceleration that was experienced. We know the initial and final velocities. All we need to find now is this delta x. We can do a couple things here. We can either do it independent of time, or we can do it dependent on time since we know the acceleration. In fact, technically, you could have solved this in a different order. All right? And we could actually find the displacement using this since it's a regular acceleration. I will leave it up to you on which one you would like to use. In my example, I used this one right here, independent of time, but I showed the acceleration. And what we'll do is we'll use that as prediction. I'll show you that you can use a different one. We have everything here, except we need to solve for displacement. So it's going to be equals the final speed plus the initial speed, quantity divided by 2, as you can see there. All you're doing now is finding an average, and then you're multiplying that by time. Okay? And that's in meters. In other words, you're applying the average speed equation. Again, that's okay because it's a straight line slope for this, and actually we have an average velocity that's pretty easy to find. And so I got the same answer when I used this formula, and it was 14.47 is what I wrote. Same idea, right? Depending on how you round. Well, that's really nice because we already knew the time for part A. That's not really the quest, is it? No. The quest is for part B. So first, we're going to have to find what the distance traveled is for part B. What is it? Well, the distance traveled, that's going to be very easy. That's going to be 100 meters minus the distance for A. And you notice I'm not worried about sig figs or anything there. Microsoft Excel is actually keeping track of everything for me. It has all the sig figs programmed in. All right? So not worried. So this is now a constant velocity. Incidentally, the speed is 11.4 now. That's going to stay the same. And now they're just going to sprint. They're going to make that mad dash. They're not increasing speed for 85.5 meters. So it's meters per second. Acceleration is 0 at this point. Hopefully that makes sense. So now what do we want to do? Well, we can, since we know that this is a constant, we can actually solve for time. If you remember, time, and I'll call this time A, or time B rather. There we go. That's going to be equal to the distance traveled during trip B divided by the velocity during B. Well, the velocity during B is just this little guy right here. That's a constant. So what's that going to equal? I'll say t equals question mark. It's going to equal this value divided by this value. That's in seconds. So very simply, we have 7.5 seconds thereabouts. Now, if you notice from my work there, I made a correction because, again, when you're plugging these things along, you got to watch those decimals. Probably hit the wrong button on that wonderful calculator of mine. I had put 74.13, I believe, down, something like that. Probably a calculator error. So be very careful with these. That was very late at night, by the way. So be very careful as you're going through. Trust Excel better than typing in buttons. So the total time, T total or TAB or whatever you want to do, is just going to be the sum of those two times. Right. So about 10 seconds. All right, moving on. So now we have the Saturn V rocket. I'm going to move this down for you. In fact, I'll keep it here and I'll just keep moving. By the way, I took that from Khan Academy. I'm sure there's lots of different versions out there, but I made it a tiny URL in case you're interested, Khan Kinematics. tinyurl.com/Khan Kinematics. So Saturn V rocket is launched straight up with a constant acceleration of 18 meters per second per second. After 150 seconds, how fast is the rocket moving and how far has it traveled? So again, as with most kinematic equations, you can usually do this a couple different ways, but let's just set some parameters here. So assuming now that gravity is working against the weight of this rocket, this acceleration is what we call the net or overall acceleration. So you do not need to think about gravity in this case. It's because it's already been taken care of. Again, as with many things, we will discuss this more in the future. So 18 meters per second per second. That's our acceleration. And we assume that this happens during the whole time from liftoff, which we assume that time equals 0 is once it's touched off the ground, not once the rocket's lit, quote unquote, but once it is touched off the ground, we start time. And so after passage of time, I would like to call it dt, change in time, but I'll just call it time. Just know that it's a delta t there. After 150 seconds, we want to know two things: how fast the rocket's moving and how far it has traveled. Now, you don't need to necessarily find one before the other. You can find speed first, possibly, and then find distance, or you can find distance first and then find speed. It is possible. The thing that we do know is that the initial speed at time 0, again, it could be an I, whatever you want your subscript to be, is what? 0. It's not one of those situations where you throw an object up into the air. You are providing a constant, we assume in this problem, a constant force upwards that is continuing to speed it up from rest. Very crucial that you understand that. And so now we can find the acceleration, or rather we can find the final velocity by using the acceleration. So I will take this formula here and remind ourselves that acceleration is, as we said before, the change in velocity over time, and then realize that the change in velocity is the final minus the initial velocity. And so since the initial velocity is 0, it really just becomes this. We say the final is going to be the acceleration times the time. Again, assuming that this is constant acceleration, which is what the kinematic equations assume. If you have a scenario where the force on an object is changing, then acceleration is changing. It means this is no bones. Okay. All right, so V final equals what? Well, let's figure it out. Should be very simple. Acceleration times time. Now look, a reminder to you, in meters per second. A reminder to you, if you do not understand what I'm doing with the spreadsheet, I'm going to upload the spreadsheet and the video. So you can de-engineer it or reverse engineer it. But that's not the point. I'm showing you a different way of doing these things. But at the very least, you go back and I've written all these solutions out for you. So you have a couple different ways of understanding these. The big point of doing this is learning how to pull information out of word problems. You've been doing this since grade school, and it always was hard, right? You pull information out of word problems and then identify what equations you can use. Now, look, I've been doing this for a long time. I understand this is usually a student's first exposure to the kinematic equations. So take your time, realize that it's all about identifying one equation where you have only one unknown. And if that means that you have to use an equation that has one unknown, you solve for that, and then it gives you a clue somewhere else, then great. And of course, you can refer to my second chapter 2 video, which goes into much more detail on that. So we have found acceleration, but that doesn't tell us, we found velocity, but that doesn't tell us how far it's traveled. And so we can again use multiple equations to do this. I have time, I have acceleration, I know the initial speed is 0, so I could easily use this equation. I used this one in the problem that I wrote out, so I'm going to instead use this equation, just to show you that you can do this in multiple ways. So it says that the final speed squared is equal to the initial speed squared plus 2 times acceleration times distance. That delta x is displacement, right? In this case, again, we're not really changing direction here, so it means the same thing. Now this v naught, right, v0, the initial speed, that's 0. We know I'm starting from rest. In some problems, the final speed is 0. Not in this case. Think about the scenario. Draw it out if you have to. It's not like we're throwing the rocket up and expecting it to come back down. We're giving it a constant force to achieve escape velocity. All right. So then we say, all right, what is D? D equals question mark. Well, let's solve for it. It's going to equal. I'll just write it out. D equals, let's solve for it. D F squared divided by 2 times acceleration. Do you agree with me? This goes away because it's 0. That divided by this uncramps D style. It's all on one side of the equation. So let's plug it in. That equals, D equals question mark. We just write it again. Why not? That equals, where's our final velocity? Final velocity squared. I'm going to put parentheses just because I like parentheses. I don't want anything to get confused. Divided by quantity 2 times acceleration. And that should be it. And this is in meters. So over 202,000 meters. Now, if you look back at my work, that is precisely what I got using a different equation. As long as you have one unknown, it doesn't matter which equation you use. All right, last one. A Boeing 747 fully loaded with all engines at full thrust. None of this information matters. An object accelerates at 2.6 meters per second per second. So acceleration is known, and that is 2.6 meters per second per second. All right. Its minimum takeoff speed is 70 meters per second. This is a plane, right? Think about this. Horizontal motion. We're waiting for lift to occur, which, if you care to have a foreshadowing of forces, we are waiting for the weight of the plane to be balanced out and then overpowered by the buoyant force, right? The lifting force. Let's see. Its minimum takeoff speed is 70 meters per second. In other words, we know that it started from rest, 0 meters per second. We know it has to reach at least 70 meters per second. And we want to know, how do we get up to that point? So it says, what minimum length of runway does the plane require for takeoff? So D equals question mark, or delta X equals question mark. Well, look, we don't have time, right? Which means we cannot use this equation. We cannot use this equation. We cannot use this equation unless we wanted to solve for time first. That's always possible. We have to use the time-independent kinematic equation. Might want to remember that. This is the time-independent kinematic equation. So we're saying D equals what? Delta X equals what? It's the same thing, right? Delta X, D, same thing. Easier to write. Well, we've solved for this before. It's going to be the final speed squared minus what? The initial speed squared, which happens to be 0, and then divided by 2 times the acceleration. How beautiful is that? Now, in the problem that I gave you, in my worked out solutions, I do this from another approach. I do solve for time first, and then I use this equation in order to find distance. And isn't it something that, besides some rounding, I get the same answer? I actually ended up with 941 meters. See, I made my corrections earlier. This was good. I ended up with 941 meters. Now, let's see. I could go back and use the average speed equation to find time. Or let's see what else I have here. What other options do I have? All I need is how much time now. I know that the runway has to be at least this. Let's see. These all have time. This is the one I used in the problem. I could now use this and this because now I have D, right? Let's see. Let me use... let's use this one, just because it's more complex and it would be nice for you to have an example. If I solve for time there, which you'll have to use this equation a lot of times, if I solve for time, it's going to be distance minus the initial speed times, oops, I'm sorry. It's going to be distance. Let me fix this. First, let me say that I can use this because the initial position is 0. So this goes away, or the initial velocity is 0. This goes away. So this is going to be distance times 2, so 2 times distance, divided by the acceleration. But it's going to be the square root of. So it's the square root of 2 times the distance, or displacement, divided by the acceleration. It's the quantity square root. Why? Because when this goes away, this is still t squared. I put everything over here. I got to take the square root to get t by itself. So let's see. What am I solving for? Time. Time equals question mark. Well, time equals square root, which in your calculator, of course, would look different. 2 times, where's our distance? Oh, we just solved for it, right? It doesn't matter what order I do this in, divided by acceleration. And hey presto, about 27 seconds. And you can see using completely different kinematic equations, I got the same thing. So what's the big idea? It doesn't matter which equations you use as long as you have one unknown for that step. So now you've gotten three very, very good, if I do say so myself, examples. I will again upload this whole Excel spreadsheet. I will release my revised solutions by hand. Feel free to study these. These will help you tremendously. And don't forget, you draw pictures, you make graphs, whatever you need to make this sensible to you.